everyone, I hope all of you are doing good, and today I am here with Work and Energy Class 9 Science. So I am Roshni from Learner Hub, the free learning platform where you can learn anything about math, science, social science, political science, geography, English grammar, absolutely for free at learnerhub.com. So what are we going to study in this lesson? Obviously, the name says it all. We are going to learn about work and energy. The moment we think about the word work, what comes to our mind? So we feel that any activity that we do, we are doing some work. For example, if I'm going for a walk, I feel I'm doing some work. If I'm going for a run, or maybe if I'm even working on my computer, I feel that I'm doing some work. Whether I'm cooking or I'm playing or I'm dancing, I feel that I'm doing some work. But does physics approve that? So let us try to understand how do we define work, or what is work in terms of physics. So we are going to complete this entire lesson in 2 videos. So make sure that you completely watch these 2 videos. The link of the playlist is given in the description below. So are we all ready? Let's get started.
Let us look at the definition of work and energy of day-to-day life, the definition which we commonly use in our day-to-day life. For example, you're playing with your friend, or you are fighting with your friend with the help of, you're throwing balloons, water balloons on each other. So again, in that case also, you will tend to, after fighting with him for such a long time, you will tend to get tired. So what are you doing? You are working. That's how we understand work, right? So definitions of day-to-day life. It says, any activity involving mental or physical effort done in order to achieve a purpose. So in layman's terms, any activity, it can be physical, it can be mental. When I talk of mental activity, you can think of the example of studying. While studying, we are just sitting on a chair. We are not moving here and there, right? So it doesn't involve any physical activity. All that is involved is mental activity. We are thinking about something, and that mental activity also tends to make us tired after some time. So it can be any physical activity like skipping or pushing a trolley. So any such activity which is done in order to achieve a purpose. So that is how we understand work as. So what do we understand energy? Energy is the strength required to do sustained work. In order to do work, we need strength, and that strength is nothing but energy. For example, you would have heard most of your moms would be asking you that, okay, drink a glass of milk. It will give you energy, right? They'll force you to eat more because that will give you energy, because you will get strength to work hard. You would have observed that when it's been long that you have eaten something, and then you tend to feel hungry. That time you're not much energetic. That time you don't feel like doing a lot of work and all, right? So that is how we understand energy and work in our day-to-day life. But what we are going to study in this lesson is that what is work in terms of science. So we will start with scientific definition of work. How does science define work? Work is said to be done when application of a force causes displacement of an object. So by now you are aware of the terms force and displacement. What is force? Force is the amount of force which you are applying on anything. We have already talked about force. Force is the cause of motion, right? In the lesson on motion, we talked about force. So when we apply force on something, and due to the application of that force, that object displaces from its position, only then we say that work is done. So we are aware of displacement. Displacement means the object changes its position. So that means, let us take a small example. There was a ball which was lying on the table. We applied some force with our hand. Due to the application of the force, the ball started moving. So the ball got displaced from this point to this point. So that means this force which we applied caused a displacement of the ball. So we say that we have done work. So work is done, right? So this is how work is defined in terms of science. So whenever application of a force causes displacement of an object, only then work is done. Okay, now let us look at some of the examples. Let us see the examples which we were using so far. I mean, in our day-to-day life, are all the examples which we consider as work, are they considered as work by science? Let us look at them. The first example, this little boy studying so hard for his exams, right? So do you think he is applying any force physically? Because here the work which we are talking about is all mental activity. So physically he is not doing anything, he is simply sitting on a chair, right? So he is not applying any force. Is there any displacement? There is no displacement. So that means no work is done. Even though this little boy is working so very hard, he is getting so tired even after 2-3 hours of prolonged study, but still, as per science, the work done in this case is zero, because science defines work as any force which causes displacement. Now let us suppose if this small boy only, instead of studying, if he pushes the book on the table and the book moves from one position to another position, we say that he has done work, because he is applying some force on the book and the book gets displaced from one point to another, right? So the first example, in the first example, as per science, work done is zero. The next example where the boy is skipping, in that case what is happening? He is applying some force, right? And because of the force there is some change in position of the rope, right? The rope with which you actually do skipping, when you apply some force, the rope keeps changing its position. So that means there is some work done. Similarly, the example of this boxing, two boxers fighting hard with each other. So they are applying force and that force is causing displacement. It causes displacement of their maybe faces, their hands, arms, and so it is actually causing some change in position. Similarly, this man trying to push a trolley, again the trolley is changing its position, the trolley is actually moving, so we say that work is done. Same scenario here also, this lady is pushing her shopping trolley, so work is done. Or this lady on a bicycle, she's riding the bicycle, so she's applying some force on the bicycle, and as a result the bicycle is getting displaced from its position. Or even in your gym you are applying some force and there is some displacement, even though you are not moving from one position to another, but the force which you are applying on the object, that object is moving. You have those pedals, right? So you apply force and the pedals move. So these are some of the examples, right? So now how do we mathematically express the work done by any object or the work done by any person? So as I mentioned, work is said to be done when application of force causes displacement of an object. So how do we mathematically express work? Work is defined as the product of force and displacement, where F is the force applied and S is the displacement produced. So the product of force and displacement gives us the work that is done. Let us now look at the units which are used to measure work, like how we spoke about force. For force we have Newton. Similarly, for work we have the SI unit joule, which is generally denoted by a capital J. So how do we define 1 joule? 1 joule is the amount of work done on an object when a force of 1 Newton displaces the object by 1 meter. That means, now as per definition also we know that work done is equal to force multiplied by displacement. So when I define, how do I define 1 joule of work? 1 joule of work is when 1 Newton force displaces an object by 1 meter. So then we say that the work done is 1 joule. Sometimes bigger units are also used, like kilojoules. So 1 kilojoule is equal to 1000 joules. Right? Okay. Now let us look at some of the examples where work done is equal to 0. For example, let us suppose there is this lady who is standing with a book of mass 2 kgs, but she is just standing. She is not moving anywhere. So do you think, forget about the scientific definition of work. What we understand in our layman's terms, do you think she is doing some work? We do think, right? Because when you are carrying some object of heavy mass for a long time, you tend to feel tired. So we say that, oh, I got so tired because I was holding this 5 kg book for 2 hours. So my hands are aching and I am tired. So we feel that we lose energy even though we were standing at the same place. But since we were carrying a heavy load, so we tend to get tired. But when we talk of science, in this scenario, the work done is equal to 0 because there is no displacement involved. The lady is standing at the same point. Even though she is carrying a heavy mass, even though she is getting tired, but still, since there is no displacement, therefore the work done is 0. Similarly, let us take another example. Let us suppose this guy is trying, there is a heavy box which is extremely heavy and it is lying on the ground, right? This guy is applying a huge amount of force on this box to make it move. So he is applying a force, he is trying his best. So do you think that the guy is not doing any work? As per our understanding, as per the layman's terms, we think that he is doing a lot of work because he is putting in so much of effort. He gets tired after some time. He loses all his energy. But as per science, the work done is 0 because the object doesn't move. Right? So, if either your force is 0 or your displacement is 0, in both the cases, the work done will be 0. So, in this case, what happens? He is applying some force F, but the displacement is 0. Therefore, work is equal to 0. Right? Now, if in this case only, if it would have been like the box would have moved even a bit, in that case, we would have said that some work is done. So work done is always 0 when either the force applied is 0, either the person is not applying any force, or the person is applying a lot of force but the displacement is 0. So in both the cases, work done will be equal to 0. Now we have something called positive and negative work. So there are two varieties of work also which we will talk about. So let us see what is positive work. When do we say that the work done is positive and when do we say that the work done is negative? So let us first talk about positive work. So we say that the work is positive when the direction of displacement is same as the direction of force. That means, let us take some examples. Let us look at this example where a vehicle gets accelerated. What happens in this case? The force which is being applied is along this direction and the vehicle is also moving along this direction. So that means force and displacement both are along the same direction. So we say that the work done is positive here. So this is an example of positive work. Similarly, if we take the example of apple falling down from a tree. So apple is falling down in this direction. So my displacement is in this direction, right? What is the direction of force? Which force is acting here? It is the gravitational force which is acting here. So the gravitational force also wants to attract it in the downward direction. So that means force and displacement both are along the same direction and we say that the work done here is also positive. So whenever we talk of positive work, the direction of displacement and the direction of force has to be same. Right? So now I think you would have guessed what is negative work. When I talk of negative work, the direction of displacement is opposite to the direction of force. Let us look at some examples. Let us take the example of the frictional force which we experience while walking. See, what enables us to work? Why are we able to work? That is because the floor on which we are walking, that is not frictionless. That is producing some resistance to our work. To our walking. So we are walking along this direction. So in this case, this guy is walking along this direction, but the floor, the ground is producing or it is giving friction in the opposite direction. So in this case, we say that the work done is negative because the force is opposing the displacement. Again, look at the example of applying brakes while driving. In the previous slide, in positive work, we saw that the force applied was along this direction and the displacement was also along this direction. But in this case, let us suppose the vehicle wants to move in the forward direction, but you suddenly apply brakes. So you apply brakes means Brakes are actually opposing the motion. So that means for that instant of time when you apply brakes, the displacement is along this direction, but you are applying force along this direction. Right? So the force and displacement are in the opposite direction. So negative work comes into picture only when the force tries to oppose the displacement. So force tries to oppose the direction in which the object is actually moving. So only then negative work comes into picture. So here the direction of displacement is opposite to the direction of force. Right? So these are the two categories of work which we have talked about. One is positive work and the other one is negative work. Now let us try to look at some of the problems based on work. So the first problem says, certain force acting on a 20 kg mass changes its velocity from 5 meter per second to 2 meter per second. Calculate the work done by the force. Okay, so in this case we are given a mass of 20 kgs. So initial velocity of the mass was 5 meter per second. Final velocity of the mass is 2 meter per second. We have to calculate the work done by the force. Now by looking at this data, can you tell me the work done will be positive or negative? What did I say? When the force tries to oppose the motion of the object. So in this case, if you see, initially the velocity was 5 meter per second. Later the velocity decreased. Right? So velocity decreased means because of the application of this force, body's velocity reduced. So that means the force was trying to oppose the motion of the body. So that means the work should be negative. Right? So let us try to calculate and see if we actually get a negative value for work. Right? Now from the third equation of motion, we know that v square is equal to u square plus 2as. So from this we can say that displacement s is equal to v square minus u square by 2a. So now by definition of work, we know that work is equal to force multiplied by displacement. From Newton's second law, we know that force is equal to mass into acceleration, and from this second equation of motion, we found that s is equal to v square minus u square by 2a. So a and a will get cancelled, so we get half m v square minus u square. So this becomes equal to half into 20 into v square is 2 square minus u square is 5 square. So this is equal to 10 into 4 minus 25. So this comes out to be minus 210 joules. So that means 210 joules is the amount of work that was done by the force, and this negative sign shows that force is acting opposite to the direction of displacement. Right? So this is my answer. Let us look at the next problem. It says a mass of 10 kg is at a point A on a table. So let us suppose this is my table. This is a mass of 10 kg. So it is lying at some point A. It is moved to a point B if the line joining A and B is horizontal. So the line joining A and B is horizontal, and now the box has been moved to this point B. So what is the work done on the object by the gravitational force? Now when I talk of the gravitational force is acting along which direction? The gravitational force will be acting along this direction. And what will be the gravitational force? That will be nothing but weight of the object, and weight of the object is m into g, that is mass into acceleration due to gravity. So this is the gravitational force, and the object is moving along the horizontal direction. So that means the force and the displacement, they are neither along the same direction. So the direction of force is this and the direction of displacement is this. So neither force and displacement are along the same direction, nor force and displacement are along opposite direction. So this is another important thing to note here. Whenever your force is perpendicular to displacement, then work done is equal to 0. If force and displacement are perpendicular to each other, then work done is equal to 0. Therefore, in this case, work done by the gravitational force is equal to 0. Now, there might be certain questions arising in your mind that why does this happen, right? But I am not going into the depth of that, because at this level you are not aware of trigonometry. You have not studied trigonometry in your mathematics. So I will not go into the detail of this. You will get to know about it when you go to class 11. So for now, you should remember that when force and displacement are along the same direction, positive work. Force and displacement along opposite direction, negative work. Force and displacement at 90 degrees to each other, or force and displacement are perpendicular to each other, work done is 0. Right? So with this, we will conclude our discussion on work. So now we will start our discussion on energy. So what is energy? Energy is nothing but the capacity to do work. Capacity of doing work is known as energy. So as I told you before also, what we think is when we have lot of energy, we can do lot of work. Now, as soon as we keep doing work, we tend to lose energy. So that means an object which does work loses energy. That is absolutely correct. An object on which the work is done gains energy. So let us take the example. Let us take the simple example of the same ball. In this case, who is doing work? This hand is doing work. So hand, why is hand able to do work? Because hand has energy. So let us suppose you have eaten lots of fruits, you have taken a glass of milk, so you have got a lot of strength, so you have a lot of energy. So since you have energy, so you are able to do work. So you are pushing that ball, so that means this hand is doing work. So hand is gradually losing energy. What happens to the ball? The ball was initially at rest. Now the object did some work on the ball, so the ball gained some energy. Right? Due to this gain of energy, by gaining this energy, the ball started moving from one point to another. Right? So that is the concept of energy. Any object which has energy is capable of doing work. But the object which does work will lose energy. The object on which the work is done will gain energy. So in this case, hand is doing work, so hand is losing energy. Ball is the object on which work is done, so ball is gaining energy, and by gaining this energy it starts to move. The SI unit which is used to measure energy is also joule, because energy and work are closely related. I mean, work is not possible without energy. If an object doesn't have energy, that object cannot do work. If an object does not do work, in that case, that energy cannot be gained or lost. Right? So work and energy are very closely related. So the unit which is used to measure work is the same as the unit which is used to measure energy. So SI unit of energy is also joule. Now let us look at the different forms of energy which we see around us. There are many different forms of energy. I have named some of them here. For example, we have kinetic energy, potential energy, heat energy, chemical energy, light energy, electrical energy, sound energy. There are so many different forms of energy. But in this lesson, we will only talk about the two forms of energy, that is the kinetic energy and the potential energy. This kinetic energy and potential energy are sometimes together known as mechanical energy. Right? So in this lesson, we are going to talk about kinetic energy and potential energy one by one. So now let us see what is kinetic energy. Energy by virtue of motion of a body. The word kinetic, what does it mean? Something which is moving. Right? So the energy which is possessed by a body by virtue of its motion. So whenever an object is in motion, we say that the object has kinetic energy. So for example, let us look at the most common example. Let's suppose when we walk, we are actually moving, our position is changing with time. So whenever anything is in motion, we say that we have kinetic energy. So this is a scalar quantity, because for this we really don't need a direction to specify it. So only the magnitude is enough. The SI unit for kinetic energy is again joule, because it is again a form of energy, right? And for energy we use the SI unit as joule. How do we mathematically express kinetic energy? That means, how do I calculate kinetic energy of an object? Let us suppose if I have an object of some mass m, and that object is moving with some velocity v. So how do I know how much is its kinetic energy? So kinetic energy is denoted by E with a subscript k. So this k subscript stands for kinetic, right? So Ek, that is kinetic energy, is equal to half mv square, where m is the mass of the body which is moving with a velocity v. So whenever you have an object of mass m which is moving with velocity v, that body has kinetic energy, and the kinetic energy in that body is given by half mv square. Let us look at some of the examples of kinetic energy. Let us look at this moving car. Now, the faster an object moves, the more work it does. For example, this car. Let us take the example of this car. Let us suppose if the car is dragging very slowly. So what do we say? We say that the car is doing very less work because it is taking a lot of time to reach from one point to another point. But if the car is moving really fast, then we say that it is doing a lot of work. It is reaching the destination from the source in a very short period of time, right? Again, when we think of kinetic energy, you can think of the bullet which is fired from the gun. The bullet is moving very fast and therefore it has a lot of kinetic energy. Or you can think of the blades of your moving fan. The blades are also moving real fast, so they also have kinetic energy. Now, such objects which has got their own kinetic energies, these kinetic energies can also be utilized for several useful purposes. So we will look into that in one of the later slides. So for now, let us try to focus on the derivation of the expression for kinetic energy. Just now I told that the kinetic energy of any body of mass m which is moving with velocity v is given by half mv square. So how do we derive, how do we know that this is the expression for kinetic energy? So let us try to derive it. Let us suppose we have an object. Let us consider that object as a ball right now. So we have this ball which has mass m, which was initially moving with velocity u. Now it starts moving with velocity v when a force F was applied. That means initially that ball was moving with some velocity u. Now I apply some force, so its velocity increases and the velocity now becomes v. So that is my scenario. So let me try to calculate the work done in this scenario. So this is my scenario. Initially it was moving with some velocity u. On application of force it started moving with velocity v. So how much is the work done on this ball? So work done is given by force multiplied by displacement. Now this work done actually causes a change in velocity from u to v. So this work done actually causes a change in velocity from u to v. Now since the velocity is changing with time, that means there is an acceleration involved. So let us assume that the acceleration involved due to this change in velocity is a. Right? Now let us make use of the third equation of motion. So what was the third equation of motion? It was v square is equal to u square plus 2as. So from this we can say S is equal to v square minus u square divided by 2a. Now again from Newton's second law, we already know that force acting on an object is given by the product of mass and acceleration. So now putting this value for S and this value for F in this expression for work done, what do we get? We get work done is equal to mass into acceleration multiplied by v square minus u square divided by 2a. So this a and a will get cancelled. So we get half m v square minus u square. Now if we assume that the object or the ball was initially at rest. So if we assume that initially the ball was at rest, in that case the initial velocity will be equal to 0. So my work done will be equal to half mv square. Right? So that means this much amount of work which was done on a stationary object made the object move. That means when the object was at rest, its kinetic energy was also 0. Now when the object started moving, it has some kinetic energy. So what is that kinetic energy? That is nothing but the work done. Understand it in this way. Let us suppose this was my ball which was at rest. Rest means kinetic energy is 0. Now let us suppose I am doing some work W on the ball. Some work W is done on the ball. And after that the ball starts moving. Right? So now that means how much work is done on the ball total? W. Because of this work done, the ball is gaining energy. So how much energy will it gain? W. Right? So when it starts moving, how much energy it has? Kinetic energy, right? So its kinetic energy is nothing but because of the work which was done on the object. I explained you before also, right? Energy contained in a body is used to do work. And when work is done on an object, that energy is utilized by the object for its motion. Right, so in this case, we can say that the work done causes the change in kinetic energy of the object. Work done on the object causes change in kinetic energy, because initially the kinetic energy was 0, now the kinetic energy is non-zero. So this change is brought about by this work done. So we can say that kinetic energy is equal to half mv square. So you understood the logic? Okay. Now let us look at some of the applications of kinetic energy in real life. The first example would be the hydroelectricity generation in dams. You would have seen there are certain places in India also where we have constructed dams. What are dams? Dams are large reservoirs of water which are used to store huge amount of water. Now this water which are stored, the water is generally stored at some height from the ground level. So like this is the picture of a dam. So you have your water stored in these places. So when the water falls down from a height, the water, since it is flowing with a high speed, so it has got a lot of kinetic energy. So the kinetic energy of the water is actually used to rotate the turbine of the generator. I mean, what is the purpose of these dams? They utilize the kinetic energy of water to produce electricity. So how do they produce electricity? They have a generator. There is an electric generator which is used to produce electricity. So in that electric generator, you have a turbine. Turbine looks somewhat like this. So when the water falls with high speed on this turbine, it rotates the turbine like this. The water keeps falling and the turbine keeps rotating. So because of the kinetic energy of the water, the rotation of the turbine is possible, and because of the rotation of the turbine, electricity is generated. Right? So what happens in hydroelectric dam? Kinetic energy of water, what does it do? It rotates the turbine and electricity is generated. Right? Let us now talk about the second form of energy, that is potential energy. So let us now see what is potential energy. The energy stored in a body by virtue of its position or configuration. Now in order to understand potential energy, let us have a quick review of kinetic energy. When we talked about kinetic energy, what happened? The work which was done on the object was used to change the velocity of the object, right? But either to make a stationary body move or to change the velocity of a moving body. Right? That is what was happening in case of kinetic energy. But in case of potential energy, whatever work is done on the body is stored in the body. Now, in what form it will get stored, that again depends. So, the energy which is stored in a body by virtue of its position or configuration. So, you will understand it better when I take some of the examples. Let us look at the example of a toy car. You would have seen that you have many such toys for kids where you have a key. You first wind the key of the car, you wind the key, and then when you leave it, after that the car moves. So that means when you are actually winding the key, you are doing some work. Some work is done on the object. So what is happening? Immediately the object is not working, right? So that work which is done on the object is stored as potential energy. As soon as you stop winding the key, the object starts moving. That means that time the object is utilizing its stored potential energy, and that potential energy is making it move. right? So the energy which is stored in the body by virtue of its position or configuration. Let us look at some of the examples of potential energy. When I talk by virtue of position, let us take the example of a roller coaster ride. What happens when you are at the top? When you are at this top, this height, by virtue of the position of the object, I mean, since the object is at such a height, the object possesses some energy. So that energy is known as potential energy, which is by virtue of position of the object. Now, as soon as this object starts falling down, the potential energy gets converted into kinetic energy, because now the object started moving, right? When we talk about configuration, we can take the example of the bow and the arrow. What happens? First, you actually stretch the bow and arrow. So when you are actually stretching the bow and arrow, you are doing some work, and that work is getting stored in the object. So when you leave it, that stored energy is getting converted into kinetic energy, and that stored energy is nothing but potential energy. So what is potential energy? It is the energy which is stored in the body by virtue of its position. Sometimes if the object is at some height from the surface, because of its position, it has some potential energy. Similarly, sometimes it has position because of the shape of the object, that is the configuration of the object. You can take the example of this bow and arrow, or you can take the example of the toy car. So due to the configuration, some energy gets stored in the body, and that energy later gets converted into some other form of energy, right? Okay. So this is again a scalar quantity. We really don't need any direction to define potential energy. It is generally denoted by EP. So like kinetic energy, we had EK. So for potential energy, we have EP. So the mathematical expression for potential energy, like for kinetic energy, we had half mv square. For potential energy, we have mgh, where m is the mass of the body, g is acceleration due to gravity, and h is height of the object. So this is the potential energy of an object by virtue of its position. SI unit is again joule, because this is also a form of energy. So now we will concentrate only on the mathematical expression of potential energy by virtue of its position. So let us try to derive this expression. Potential energy is equal to mgh. From where do we get this expression? Let us suppose we have an object. Let us say again we have a ball of mass m, which is taken to a height h from the ground. Let us suppose this building is of height h, the height of this building is h, and we have somehow taken this ball to the top of the building. Okay, so now this object which is stored at this height has gravitational potential energy. Why it has potential energy? Because of its position, which is h from the ground. And why it is gravitational potential energy? Because the gravitational pull of the earth at every moment is exerting some force on this object and is trying to attract it. Correct? Now, in order to take this object to the top of the building, some force would have been needed. I mean, the object would not have gone by magic to the top of the building. In order to make it reach the top of the building, some force would have been applied. What would have been that force? That force would have been the force which would have opposed or which would have overcome the force of gravity, right? So, we can say that to take the ball to the top, some force would have acted, right? So what was that force? That force is nothing but the gravitational force, that is the weight of the object, which is given by mg. So ball gains the energy. So now whatever work was done on the object, that work done is stored as energy, right? So ball gains energy because the work was done on the ball. So the object on which work is done, that object gains energy. So therefore ball gains energy. Now what is the gain of energy? The amount of energy which ball gains is equal to the work done on it. So work done on the ball to take it to this height is force into displacement. What is force? Force is mg. Displacement is nothing but height of the building. So this is the work which was done on the ball to take it to the top of the building. Now whatever work was done on the ball is stored as potential energy inside it. So therefore we can say that potential energy is equal to mgh, because whatever work we did on the ball to make it reach the top of the building is stored as potential energy, and as soon as the ball falls, the same potential energy will get converted into kinetic energy. Right? So now you're clear how did we get the expression for potential energy?
So children, let me know, how was this video? Did you like it? Did you learn something different from it? Did this video help you to solve questions, to understand the concepts? Do not forget to share your feedback in the comment section, because we will be more than happy to hear from you. And if you really like the video, do not forget to share it with your friends. I will meet you all very soon with a new video, with a new topic. Till then, stay home, stay safe, take care, bye-bye.